So this is what I'm going to talk about, tracing how is a mass distribution compare with the underlying distribution of light and stars and baryons, if I can get to all of that. It's addressing it. It's, of course, related to the bias directly. You want to see how the mass and the stellar mass relate to each other and galaxies fit in halos. But it's not looking specifically at halos with all the way we define halos or central and satellites and so on. It's looking directly at observations in a simple way, looking at the mass distribution from lensing, looking at the stellar mass from the light, and looking at the baryons from the various places where we can detect the baryons and see how they trace from very small scale all the way up to very large cosmic scales. And it's on average. We're looking at it on average on large scale. And it's very interesting to see the results where we see that the mass and the light and the stellar mass trace each other remarkably well on large scales. So the usual intuition that we all think about started in the 80s, maybe even before, where the mass is obviously more diffuse than the light, but we always think that the mass is more dominated as we go from small system to large system, from galaxies to groups to clusters. The mass per unit light keeps increasing as you go to large scale. This is not correct. That's correct only on the small scale of galaxies, galactic halos. Once we reach to the larger scales of groups, clusters, large-scale structure, everything starts following each other remarkably well. So here is work from done with Andrea Collier here, looking at the mass per unit light as a function of scale within a given radius as a function of scale, radius, all the way from very small scales of 20, 30 kiloparsecs, 3 orders of magnitude up to 30 megaparsec. This is done from the masses are obtained from weak lensing analysis in the Sloan Digital Sky Survey. These are max BCG groups to clusters, starting from the smallest groups of n of 3 or so, all the way to the richest clusters. They are stacked by richness. Weak lensing was done by Johnson and Sheldon and so on. So those are the weak lensing analysis we used. So tracing the mass, so it's the mass BCG cross-correlation. So you look at the weak lensing analysis cross-correlated with the BCG position. It doesn't matter if the BCG is center of group, cluster. It really doesn't matter to us. It's how is the mass distributed around these galaxies. They mostly sit in centers of groups and clusters, but it really doesn't matter. So we look how the mass is distributed with this cross-correlation. We do the same for the light. So it's the light BCG cross-correlation using all the galaxies down to about 0.19 L star. Those are the tracers for the light. And we do the same thing with the cross-correlation. So you have the mass from 20 kiloparsecs to 30 megaparsecs, the light in the same scale, stacked on different richness, and we look how the mass per light is distributed. Ignore for a moment the 3 upper curves. Let's look at this. This is a straight data. The 3 different curves are just bunched by richness. These are the lowest richness bins. It's actually several bins together, but we keep it simply the lowest, the richest clusters, and the intermediate clusters. And you see that the mass to light starts from small. You're at the center. You're at 20 kiloparsec. You're sitting on the BCG. So it's just a galaxy. You start from 10, 20. It keeps increasing to about 100, 200, 300. That's just the halo of the BCG. Within the group or cluster, doesn't matter, but you're just measuring the usual halo of the BCG. It's what?
Is the ICL included in this or no?
We also add the ICL in the final. In this particular one, I don't think so, but for the final results, I'll show you the ICL is added. So it keeps rising because you sit on the BCL and grow. The mass keeps growing. It's dominated by light, so you start small, and then the mass starts dominating. But the main thing is that at the order of few hundred kiloparsecs, 200-300 kiloparsecs, everything flattens out. Mass and light follow each other quite remarkably well. This is all due to the BCG. If we just pull, because you sit on the light, so the light pulls you down, M over L is small, and if we just pull the BCG out, just the light, these are the curves. So you see, this is all the BCG, which is what you expect. So you see, this is flat. It's actually rising because we only pulled the light. We didn't pull the mass out. You see that for the smallest groups, the mass to light rises. It's the integrated within the radius, rises slower than in the rich clusters. Rich clusters reach the flat, constant mass to light ratio, which is representative for the universe. It goes all the way to cosmic scale very quickly at 200, 300 kiloparsecs. And that's because the BCG, this is all the BCG, is less important in the rich clusters than it is in the small group. And in fact, this is exactly why we are all used to, and we've seen it this morning several times, when you look at the stellar mass to total mass, this shape that, you know, the high mass end, everything, the stellar mass falls down. It's just the BCG. It really doesn't tell you much about the cluster. It only tells you how the BCG grows, and the BCG and the rich clusters grows much less than the cluster itself grows. So everything grows by mergers. The mass gets merged and grow quickly for the cluster. The BCG also grows by merger, but much, much less efficiently than the whole cluster. That's why when you look at the stellar mass to total mass, you see this fall, which doesn't tell you anything, in my opinion, other than how the BCG grows in those clusters. In the groups, it's less, they're less important. And therefore, you see it's more dominant, and it grows slower because the BCG light affects it. Yes, I'll show you in a moment without the BCG, because if you think about a BCG with 2, 3 tiny little galaxies around it, that BCG is the whole luminosity of the cluster, and it will continue to, it will affect the integrated to larger scale. So if we remove the, just the central, this is still the integrated. Here it's in units of not megaparsec, but in units of R200 critical. So this is R200 critical. We remove the BCG, and we remove just the mass, the lensing mass within 50 to 100 kiloparsecs, just to see what happens when we remove the center. And you see, again, pretty flat. You see a slight trend coming down. The black line of the trend, which seems to represent the trend in the data, is simply the stellar population trend in groups and clusters. Stellar population means the mix of old and young galaxies, the density morphology relation, if you wish, the second parameter, color, age, and so on, that goes into the mass per unit light. And we actually see it in this in the data. So we see the trend of the stellar population, and other than that, it's flat. That also means that the reason that the mass follows light approximately, other than trend, is that the mass simply follows the stars, or actually the stars, which is only 1%, follows the mass remarkably well on average, and it flattens out.
So when you calculate the light, to which kind of luminosity?
0.19 L star. All galaxies to 0.19 L star. 0.1. 0.19
Oh, 0.19. Sorry.
L star.
So then, but many of your BCGs actually are located quite far away, right?
Far away. In redshift, it's only to 0.3. Those are all clusters 0.1 to 0.3. It's about 160,000 groups and clusters.
This is a detail. So basically, your lensing has a window, redshift window.
Yes.
And then, depending on which kind of magnitude you cut, then the galaxy redshift distribution also has a
No, it's 0.1 L star in absolute magnitude. Absolute magnitude.
Still, the window has to, otherwise you do cross correlation, one window.
Right, but we count it to 0.1. The threshold for all, it's in a volume limited 0.19 L star. We can talk about the details later. It's also discussed in the paper. So this is the integrated. You see the dependence, you see the stellar population. If we want to then look at what is the distribution and forget about the central region, the BCG, it's clearly a separate something, the BCG is a unique region. So we look at the local mass to light at any given point. You have big or scatter, but now it's independent of the BCG. You just look on average at any point. How is the mass distributed? How is the light distributed? How do they relate to each other? As a function of R over R200. And again, you have loud scatter, but all systems are the same. Also, this flatness with a small trend of the stellar population. And what I found quite remarkable is, and that's independent of the BCG, look at where we start. We start at about 0.3 of R200. So we start at like 300 kiloparsecs or something. We start so inside clusters, and I was surprised to see that, inside clusters, once you are outside of the BCG, the mass distribution follows the light distribution, other than the stellar population trend, remarkably well. And I'll show you an image. If you think about it, all the beautiful lensing analysis that is done really does trace light remarkably well. But that's what it shows it quantitatively. And again, it starts even inside groups and clusters at small scale, like 300 kiloparsecs, which is about the virial radius, or R200, of an L-star galaxy. And it continues all the way to 30 megaparsec. You can look at it in a different way. Simply look at the density, the mass profile from the lensing for all the richnesses. Again, all the way to 30 megaparsec, and look at the remarkable agreement for all the systems. The light distribution, the number of galaxies distribution, same thing. Here's a comparison from one of the recent Hubble Space Telescope CLASH clusters that does really beautiful lensing analysis. Here is the cluster. This is the lensing analysis of the cluster superimposed on the galaxies, on the light. And you see, and here is a decomposition of the analysis, the model decomposition here for individual galaxies and the overall smooth galaxy mass. And you see that the mass and the light trace each other remarkably well. And that's what we see in the analysis. Now, the galaxies themselves, their halo may be all stripped off inside the cluster, but the mass is still there in a smooth distribution, or not in a smooth distribution, we cannot tell, but it still follows the light distribution. One thing that I also found interesting, this is the same results, the mass, local mass to light as a function of scale. How much of the mass that we see, the light all comes from the galaxies plus the ICL, and we add the ICL here, the intracluster light. The mass, the question is, the light comes from the stars, from the galaxies. Where is the mass? Usually the concept is the galaxies have less mass, clusters are bigger halos, have much more mass than the sum of all the galactic mass. We believe that most of the mass comes from the galaxies themselves, that the cluster does not have much additional dark matter other than the galaxies. If we take galaxies with their own, individual galaxies with their own mass to light ratio, for example, from our own Milky Way galaxy, Andromeda, where the mass is measured to within, not very accurate, 30%, 40%, and we take the high numbers from the recent observations, like 2 or 3, 10 to the 12, up to 300 kiloparsecs, and one can even go larger, I mean to larger scale. You get the mass per unit light. It's a high number. It's about 100 mass to light ratio. You take it for ellipticals, which is a higher value by a factor of 2 because they are older galaxies. You combine it with a density morphology relation, the mass to light of galaxies, elliptical spirals combined with a density morphology relation. You add what we observe as 12 or so % gas to the systems, and that gives you the blue band. And this is just mass from galaxies themselves, a mix of ellipticals and spirals, plus a little bit of the gas that we know exists there. We observe it. And you don't need additional dark matter any place, in groups, in clusters, in filaments, in large-scale structure. It's just a combination of all the galaxies in those systems, in the groups, in the clusters, in the filaments, in the void. We think we'll find very little mass in the void. So it doesn't mean that there isn't 10, 20%, a little bit more mass, but not very much more mass. Most of the mass, we think, is coming simply by combining the tens, hundreds, few galaxies with their mass, with their light, with the cluster light and the gas. And that's if we assume the mass that we measure for Milky Way, Andromeda, and from some of the lensing for elliptical galaxies. So that's a separate thing. We can also get from this analysis, convert the light to stars and look to see what the stellar fraction is and how does that depend on scale, on mass, and so on. Again, we are familiar with the stellar mass fraction that goes like that drops at very large scale. Again, that's just the central galaxy. Here is the stellar fraction. Flat, couldn't be flatter than that. So how do we get the stellar fraction? The stellar fraction, the observed typical stellar mass to light for ellipticals and spirals. We take it with the mixture of observed ellipticals and spiral following the density morphology relations and divide by our observed mass to light function. It's all observation. There are no assumptions here. I mean, there are no major assumptions here. The what? The different colors?
Yeah, the different lines, they all peak 3R200, and in the following plot you have a minimum of 3R200.
Yes, I was wondering a lot. Why is everything, you mean like the peak here? I was wondering about that quite a bit. I think maybe what's happened, I don't know what the answer to that is. You know, if you want, it's kind of flat all the way here. That also suggests that the radius where you see influence of red galaxies is larger, as we said before, and was discussed before, goes to maybe 2, 3 R200. But I think that may be the region where you have the infall, what did you call it, the splashback, backsplash, radius? Say it again?
That was for 10 to the 12, so the Maxwell was really small one. The cluster scale here was you expect it to be.
Yeah, but this is right, that's about 3 R200, which is roughly where the splashback radius is for these systems. That's approximately what it is. It's R200, 2 or 3 times that, so it's roughly in that region. It may be related to that, or it may be just flat and fluctuation. I don't know, but I was wondering because they all show that, which if you have some good ideas, I don't know what it is, but it's interesting. I think the error bar, I have it on the other plot, I think it's roughly the scatter that you see among the points. So there are large errors. It's not a 1% measurement, but the overall picture is quite different than the picture that we are used to think about. So we can get the stellar fraction simply from this is observed, combined with the density morphology relation. This we just showed the observation. We divide the two and we get the stellar fraction. This is the local stellar fraction every place starting from about 0.3 of R200 in all the system, from the smallest groups to the richest clusters and going all the way to 30 megaparsecs. And it doesn't matter if it's in groups or clusters or even if it's just BCGs or LRG. It's just the same environment everywhere, and it's 1% everywhere. So the stellar fraction is about 1% everywhere other than in the very central regions. The band here is the observed cosmic value of stars, 1%. Cosmic stellar fraction is 1%. And it is, I found it quite remarkable. And by the way, this low peak corresponds to the high peak there because it's related. So it's everywhere. It's one on average. You sum it up. Obviously, faint little galaxies will have much less stellar fraction, but this is average, and it's on average. It's everywhere the same, except right at the center where you sit on the BCG, you have lots of stars being generated. And you can see the LRG here. This is a stellar fraction integrated within a given radius. So you see that for rich clusters, it's about 1% everywhere, and as you get closer into the LRG, again, this will be about 200 kiloparsecs, well, it starts rising because you are hitting the LRG. You have a lot of stars in it. For the smallest groups, the stellar fraction is higher only because the BCG is dominant in the small group. You come to a BCG that is dominant in small group, and the stellar fraction is higher. And that's what gives you in the usual central stellar mass versus total mass fraction, this fall off at high mass is simply that you sit on the BCG. You only measure the central and the star formation there. But if you look at all of it, and that's within R200, if you look at it at within 3 times that, which is roughly the caustic value, they are similar. It's a little higher in group, but they are similar. And as you go to larger scale, it's just 1% in everything. Anyway, these are some of the results. The mass follows light. It's the same in all environments, from the smallest group to clusters all the way to cosmic scales, and even inside all these systems. And it starts at 300 kiloparsecs, or so, a few hundred kiloparsecs, except for the BCG. We see the stellar population effect. We see the constant stellar fraction at 1%. And one thing that I was wondering, how come the 1% knows exactly where all the mass is? Because the stars are about 1% of the total mass, the mass in stars. How come it follows it so incredibly well? There's something there, it's telling us something. And one thing that I want to show you and finish with that is, I think that what's happening, and that's what we're doing now, is that originally, of course, the baryons fall into all the dark matter halos with the cosmic fraction of about 16% or so. And we thought that we don't have the cosmic fraction if you go, when you go from galaxies to groups to clusters. We are missing a lot of baryons, especially in galaxies and then in groups. But now we are detecting a lot more baryons in them. So what I'm going to show you, that we think that the cosmic fraction of baryons is about there around galaxies, groups, clusters. If you go to the large enough radii of the virial or a little beyond the virial, the baryons are mostly there. They're still flowing in and flowing out. They're a mess. It's gas, hot gas there. But a small fraction of this, on average, cool to form stars. And that gives you some constancy between the baryons, the stars, and the total mass. And I'll show you that one in just a moment. And the other thing that I showed you, that if we take the mass observed in our Milky Way, in M31 and so on, we think then, therefore, it suggests to us that most of the dark matter in the universe is simply located in the large halos of galaxies, and then all the other systems, group, clusters, filaments, voids, are just the sum of them in the mass and in the light. Now, of course, there is the gas added, there is intracluster gas, all of that is there too, but most of the mass comes with that. We also get omega, of course, from that, which is consistent with the cosmology. Let me show you about the baryon. Of course, one talked about the missing baryon, that if you go from small groups to clusters within R500, you have very little gas. But if you go to the virial radius, it increases. If you add the stars, you reach the cosmic value. And if we add the circumgalactic medium now observed recently around galaxies from many measurements, including the Hubble cos absorption lines. This is from the work of the L-star galaxies absorption lines. This is their budget for the circumgalactic medium, for the cold, for the warm, for the stars, and it's almost the cosmic value. And when we put it all together, and that's work that has not been written yet with Benjamin Cook, my student, when we look at the baryon fraction, the gas plus the stars, all the way from L-star galaxies, again, we don't include the faint galaxies, we don't observe them, but from L-star galaxies all the way to the richest clusters, you see that it's just about the cosmic value if you go to around the virial radius or slightly above. So we think, first of all, we don't think there are many missing baryons. And I think that if you have a constancy of baryons falling in cosmic fraction, some of them cooling off, 10% of them cooling off, forming stars, it could give you this 1% in the stars.